My name is William Lane. I'm here to present a finite state approach to interactive transcription. This is work completed by myself and Professor Stephen Bird at the Top End Language Lab at Charles Darwin University in Darwin, Australia. So the bulk of this work took place in remote Northern Australia in collaboration with speakers of the Gunwingu language. Gunwingu is a polysynthetic language spoken by about 1,500 people in this West Arnhem region of the Northern Territory. Over the course of several years, we have been working with the community on language technology projects to support locally relevant goals such as language learning, transcription, and knowledge sharing. Locally relevant language activities include transcription of recorded speech for the purpose of making the knowledge captured in these recordings available to the local community. However, the Gunwingu language is considered low resource in the mainstream NLP sense, in that there is not a lot of annotated speech or large written corpora available from which to build robust machine learning models. This leads us to our two-part research question: how can we leverage the resources we have available to us to support locally relevant goals? In our case, the Gunwingu language has been studied by linguists for many years, and we have extensive grammatical descriptions, but still relatively few texts and lexicons, which are probably a more traditional language technology resource. So can we leverage the grammar to produce texts and lexicons, basically a strengths-based approach? And again, to produce artifacts and language technologies that the community is interested in. So for example, indexing texts for search, building lexicons for language learning. In previous work, we describe a process for interactive transcription, which enables human transcribers to maximize their effort towards producing useful orthographic transcriptions. The interactive transcription process is built on concepts from sparse transcription and local word discovery, which are described in depth in these two separate publications. In brief, the interactive transcription begins with partial orthographic transcriptions of audio. And then, so we have partial transcriptions of audio, which we feed to a local word discovery system, which takes those partial transcriptions, treats them as anchors from which we can make predictions or extend the transcription to fill in the gaps in the transcription, or at least make hypotheses for what could fill in the gaps in transcription. These automatic hypotheses can then be manually confirmed by fluent speakers. These confirmations can be used to populate a lexicon, which can then be automatically applied to a wider speech corpus to find other exemplars of those confirmed segments in the wider corpus. We can have those confirmed by fluent speakers as correct lexical entries, as correct exemplars of a particular segment. And that contributes to a more dense version of the original sparse transcription. So you can see it's, for lack of a better term, data flywheel. It's sort of an iterative process for arriving at more and more dense transcriptions. And again, this is built on Stephen's sparse transcription framework with some extra modifications for generating automatic hypotheses. And so that's previous work. We've described this process as interactive transcription. To make this task a little bit more concrete, we give an example right here. So task G is how it's referred to in Stephen's sparse transcription paper. But basically, if we're using Gunwingu as an example, the transcriber would recognize pronominal morph ngari from audio and place it in a phone stream, or basically align it to the audio. We heard ngari, but we have these other sounds that came afterwards and we didn't understand what it was. But we heard ngari, we're pretty sure we heard ngari. At this point, our lexicon is empty still because we need to have hypotheses confirmed by fluent speakers before we actually add them to the lexicon. So we have Ngari, we have a hypothesis, and local word discovery can then use that as an anchor and extend and say, okay, well, given that this is Ngari with high confidence, perhaps next to that anchor, it's this these other morphs that could combine with Ngari to create the word Ngari Bimbum. If this hypothesis is confirmed by a fluent speaker, then the lexicon gets populated with the constituent morphs of that word. And those morphs can be used because we now have offset information for each of these morphs. Those can be used for word spotting, what Stephen calls task S in his sparse transcription paper, to find other exemplars of these words in the wider corpus. So if we're looking at the same utterance here, we find that maybe BIM can be spotted by word spotting techniques, in which case BIM becomes another anchor from which we can again do local word discovery and extend BIM into a full word hypothesis, which can be confirmed, and then the constituent morphs again go and populate the lexicon, and the cycle continues to get more and more dense transcriptions. That's the idea of interactive transcription. That's the general workflow. Oh, oops. So as I mentioned previously, interactive transcription relies on an automatic task, which we call local word discovery. For a polysynthetic language like Gunwingu, this means that our sparse transcription contains a lexicon of morphs and their offsets that we are confident we recognize in a given audio. Local word discovery is the task of automatically generating hypotheses for complete words based on the locus of known morphs. Based on the locus of known morphs and conditioned on the phonemic information which we can derive from the audio. Our initial implementation of local word discovery involved using finite state models to decode the output of a noisy phone recognition model. However, a weakness of this approach was that it relies on user-provided alignments of anchor lexemes in the speech stream. As you can see here, how do we know that Kabiri occurs here? We assume that a user put it there, somebody aligned it there manually, right? While there may be benefits to assuming the user has that kind of fine-grained control over the alignments, such work can be arduous. Which brings us to the work that we're presenting here. In this work, we propose a new finite state approach to local word discovery, one which jointly aligns anchor lexemes and predicts full word completions without requiring the user to provide alignments explicitly. Functionally, the biggest change is the input is a phone sequence derived from the audio and known lexemes, which are in order but unaligned. We took inspiration from optimality theory, where there's a gen function which basically generates candidate predictions based on this input. And basically, it aligns and generates possible predictions based on all possible alignments. And then we use an eval function to then filter that set of results, or that list of results, to best candidates. And the way that eval function works is through what we call the logic of how we rank and prioritize the list of generated results can be visualized through this constraint tableau. So let's see. So the logic of the eval process can be seen here, where generated candidates are listed in column 0, and the ordered constraints, which these candidates are ranked against, are listed in row 0. Violations of a particular constraint are denoted by these asterisks, and candidates are eliminated from consideration as long as there remains at least one valid candidate, which can move on and be evaluated in the next round. So these 3 candidates here, Manme, Biridokmi, and Biridok Marin, they all violated a constraint called anchored. Basically, were these anchored at the locus of a known lexeme? No, they weren't. Because these ones actually, the rest of the candidates actually are anchored, we have a valid set that can move on to be evaluated against the next set of constraints or the next constraint. So these get eliminated and the ones that survive move on to be evaluated. And we basically go through the Tableau, through the ordered list of constraints until we have no more candidates that can proceed. And so the last remaining set of candidates is our last set of candidates. And here we see we end up with Kabiri Dukmiri, Kabiri Di, and Kabiri Dong, which of the three, Kabiri Dukmiri actually is in the gold transcription. The other two are not. So our paper provides a complete minimal working example of local word discovery with joint alignment and filtering. So if you plug this into an XFST parser, it can compile this and it can run basically a toy example, which then can be extended. Obviously, in the interest of time, I won't go through all the details here. In terms of results, we tested this implementation of local word discovery on a test set of 126 Gunwingu utterances collected as part of a tour of the Gabelbarnumio outstation in West Arnhem. To simulate a sparsely transcribed corpus, we manually annotated the top 20% most frequently occurring morphs across the collection. These served as our initial set of anchor lexemes. Feeding this to local word discovery, we found that 12.7% of all predictions were correct full word extensions of the anchor lexeme. Further, 38.2% of predictions were at least partially correct completions, meaning that the model was providing suggestions which would hypothetically lead to a full complete completion, perhaps in further rounds, further iterations of local word discovery. In terms of the spread of correct predictions across spoken documents, we found that 57.9% of utterances contained a full correct predictions, while 66.7% contained at least partially correct predictions. Further, this version of local word discovery produces a more manageable number of predictions per utterance. You can see on average, this second version produced six predictions per utterance, while the original version had 64. So you can imagine a user would have a much easier time looking at 6 predictions and saying, yeah, all of these are wrong, or this one's right, versus looking at 64 and trying to determine which one was correct, or if there are several that were substrings of something that's correct. It's a much harder task when you're flooded with possibilities. There are, of course, limitations. In order to align anchor lexemes to the phone stream, this finite state algorithm requires dynamic compilation of both the phone stream and the anchor lexemes as FSTs. Those are the input to the system, and so they have to be encoded as FSTs. And so that has to be compiled at runtime as the user provides input every time. The other components of the network are static, so they don't have to be compiled at runtime every time there's a new input. But current implementations of this are a bit slow compared to the first iteration of local word discovery. And so I wouldn't say we've settled on a great implementation of this just yet. So that's something that's sort of still in progress, still a workshop item, I would say. In summary, we proposed a novel approach to interactive transcription via local word discovery algorithm, which eliminates manual human effort to align anchor lexemes. The approach leverages what we have available to us, that is speakers and a formal grammar. And it reshapes the local human participation to focus on identification of keywords rather than laborious and unmotivated phone transcription. We hope in the future that this work can be integrated with collaborative interactive transcription systems, such as publication we had last year and a newer iteration of the same system made by Matt Bettinson and Stephen Bird in 2022. These are the papers sort of referred to and sort of the background to some of this work, including the newest Bettinson and Bird's Learning Through Transcription paper, which is quite excellent. So yeah, that's I feel like I was talking super fast to try to hit the time limit and I still went over, but that's what I have.
Thank you very much. No, you're perfectly on time because we had some troubles at the beginning. And we've got, I think, 3 minutes for questions. So who wants to ask a question? Please raise your hand if you want to ask a question. Perhaps someone in the offline audience wants to ask a question. Unfortunately, I can't hear. So if someone in the offline audience wants to ask a question, please come up to the notebook laptop and ask your question.
Sorry, no question on site.
Okay, then I've got a question. Actually, I wanted to ask you about the actual work with native speakers. How did this new method help you? Did it really make your transcription process faster? And can you estimate like the rate at which it made your transcription work in the field faster and perhaps more convenient for the native speakers?
Yeah, that's a great question. So the first iteration of local word discovery, we use that more in the field, and the whole process, we use that more in the field in this version, because this version, again, as I said, the implementation was a bit slow to be practical. And so the focus of this approach was to try to sidestep or eliminate the more arduous work that the people in the community that we were working with, like, they don't want to necessarily sit down and do dense transcription with you. They want to talk about what they heard. They want to basically have conversations about the audio. And so an insight that I derived from experience working in the first version of local word discovery was that with this system, I can sit and I can have the laptop and we can have it in front of us and I can drive the process, but it enables me to basically have conversations about what we heard. Like, we can hear something and I can read the suggestions on the page and I can ask the question, did they just say that here? And then the speaker will say, oh yeah, they said that, and they'll explain the word and the context, but I got the confirmation. I need to push the button to say, like, yes, that's confirming the hypothesis that the machine had. And so I wouldn't say, because we didn't directly evaluate whether or not this saves time, I wouldn't claim that this saves time. I would claim that this tries to sidestep some arduous aspects of transcription. And just from those trials with the first version of local word discovery, I would say, like, tentatively, yeah, it feels like it does. It feels like it makes the whole session more enjoyable because we're sitting back and having a conversation with the people we're working with, rather than trying to get at something dense and completely accurate right up front. I would say it helps prioritize work as well, because I can sit back and interact with the system and do my first best pass at this sparse transcription. And then when I do have time to go out into the field, or someone has time to come into the office and work with me, then again, it's a sit down, it's a conversation, and it's me clicking buttons to confirm hypotheses over the course of a conversation. So again, I wouldn't claim that this saves time. Maybe it does, but I've never measured that, and I won't claim that. And again, for this version of local word discovery, the implementation needs work in order to integrate it into a system. So yeah.
Yeah, thank you. That's a great system, and I hope it will help us in our field work, because yes, transcription is known to be quite tedious and not very pleasant for most speakers. Thank you very much again.